Hello and welcome everyone. This is Asif Khan from Georgia Tech, and it is my great pleasure to be back at ISAF. So in my presentation, I'm going to talk about ferroelectricity in the context of microelectronics. So microelectronics is undergoing a new wave of exponential growth. And the goal of my talk is to give you my perspective on the role that ferroelectricity will be playing in microelectronics in the coming years and decades. So with that, let me get started. So microelectronics as a whole stands on over 40 years of innovation and excellence. For example, the iPhone that came out in 2018 packed approximately 7 billion transistors. So this is a testament to the excellent job that industry has done over the last couple of decades in making not the transistors smaller and smaller and making them even more powerful. Now going forward, what is the innovations that are happening in microelectronics? One can draw from many different examples, but I choose to take an example of wafer scale integration. For example, over here, this gentleman is holding a piece of silicon. Now, the amazing thing is that this entire piece of silicon represents one chip that packs over a trillion transistors. So this is an example of wafer scale integration that has been envisioned since 1980s, but it is only achievable now. Again, a testament to all the innovations that are happening in microelectronics. All right, so what is the key driver for the innovations in microelectronics? So we hear a lot about the fourth industrial revolution, which is currently going strong. There has been a lot of excitement around the upcoming paradigms such as augmented reality, autonomous transportation, smart cities, personalized medicine and healthcare, so on and so forth, many of which are powered by the advancements in AI and machine learning. However, the key realization here is that all of these exciting technologies are going to be supported by the microelectronic hardware. In other words, innovations in microelectronics hardware is necessary to materialize all these exciting visions. Now, we also hear a lot about the Moore's law being dead, but the industry perspective is that Moore's law is not dead, it's not even sick, it is well and alive. The dimensional scaling might be ending pretty soon, but there are many tricks that can enable electronic hardware to get more and more powerful and efficient, possibly at a speed that than that it had happened in the past. Now, why are we talking about it at ISAF? Because of two reasons. The first thing is that I believe ferroelectrics will play a central role in microelectronic hardware more powerful and efficient. It will be a key driver for innovations in microelectronics. Second point is that there is, I believe, a strong need for the ferroelectrics community and the semiconductor community to come together to solve some of the critical challenges to enable ferroelectric technologies in the mainstream semiconductor platforms. So in the rest of the talk, I'm going to explain all these things in a little bit more details. Now let's dig deeper. So a ferroelectric material is characterized by hysteresis loop in terms of the polarization versus electric field characteristics. Now, if in the absence of an electric field, the ferroelectric has two remnant polarization states, and this is the basis for the non-volatile memory applications of ferroelectrics. An equivalent description of a ferroelectric material is in terms of the free energy landscape with respect to the order parameter polarization, which has a double well shape. Now, this energy minima in this double well energy landscape corresponds to the remnant polarization state. Now, things get quite interesting if one focuses on this energy barrier region, which separate these two energy minima. So, a capacitance of a capacitive material is defined as the inverse of the second order derivative of the free energy with respect to the charge or polarization. Now in this energy minima region, this derivative, second order derivative is positive, which means that in these two regions the capacitance is positive, but in this barrier region, however, the capacitance is negative. Now naturally this region is energetically unfavorable because it's an high energy state. So if we want to put the polarization over here, the polarization will spontaneously roll downhill to one of these positive capacitance state. So in other words, this negative capacitance state in a ferroelectric material is unstable. So how can one access this negative capacitance region in a stable experiment? In other words, how can one stabilize this negative capacitance state? So one way of stabilizing this unstable state is to fabricate a heterostructure containing a ferroelectric layer and a paraelectric or a dielectric material. So the stabilization mechanism can be understood by looking at the energy landscape again. So the blue curve over here represents the double well energy landscape of a ferroelectric material, and the black curve over here represents the energy landscape of the paraelectric material. Now, within a certain set of assumptions, the total energy of the entire heterostructure will be a sum of this blue and the black energy landscapes. And if we choose the parameters, for example, the thicknesses of these individual layers correctly, then the energy landscape of the entire structure will have a single minima. Now again, since both the ferroelectric and the paraelectric materials are in series, both of them will have the same amount of charge across them. So if to minimize the energy, the total charge of this heterostructure will lie in the minima of this red curve over here, and that will also correspond to the fact that the polarization of the ferroelectric material will also sit on top of this energy barrier, meaning that the ferroelectric will be in the negative capacitance state. Now, from a macroscopic point of view, what will be the signature that the ferroelectric material is actually stabilized in a negative capacitance state? So to understand that, one can resort to the classic law of electrostatics, which says that if we have two capacitors in series, the total capacitance will be smaller than each of them. So for example, if we take a 2 picofarad and 1 picofarad capacitor, two capacitors, then the total equivalent capacitance will be 2/3 of a picofarad, which is smaller than each of them. For example, on the other hand, if we take negative 2 picofarad and one capacitor which is 1 picofarad, put them in series, then the total capacitance will be 1.5 picofarads, which is larger than the positive capacitor, which is 1 picofarad. Essentially, if we have ferroelectric stabilized in a negative capacitance state in a heterostructure with a paraelectric dielectric material, there will be an enhancement of capacitance. So what problem does negative capacitance address? It is the energy efficiency electronics. For example, data centers already constitute anywhere between 1 to 5% of global electricity demand, and this percentage may go up significantly over the next couple of decades. And there are always new disruptive technologies that are coming up. For example, crypto mining in 2018 constituted 1/3% of global electricity consumption. So how does negative capacitance solve this challenge? To understand that, in the very first place, the energy efficiency is a challenge because as we were scaling down the transistors, we could not make them as much energy efficient as we wanted them to be. The reason is that the carriers that are there in the semiconductor channel follows what is called the Boltzmann distribution, and as a result, to turn on a transistor, we need a minimum amount of voltage, and this voltage we cannot reduce however much engineering that we can do in a traditional transistor. Now, the way negative capacitance can help is that if we replace this oxide material in the in a transistor, then with a negative capacitance material, then we can have a capacitance enhancement in the transistor. The easiest way of understanding how it can reduce the voltage is that since this negative capacitor over here will cause an enhancement of the overall capacitance, that means that we can have more charge in the semiconductor for a smaller amount of voltage, and as a result it can reduce the power supply voltage below the fundamental limit that is set by the Boltzmann distribution, and in doing so it can address the energy dissipation challenge in transistor. And this was essentially the concept that was proposed in 2008. Now, we started working on this concept of negative capacitance and to demonstrate experimentally. So what we did in our very first experiment is that we took the prototypical ferroelectric lead zirconate titanate, and as a paraelectric material we took strontium titanate and made a heterostructure out of it. And then we measured the capacitance. So here, this is the most important result that we in our first experiment. So we took 28 nanometer of PZT and as the paraelectric material 48 nanometer of strontium titanate. And if we look at this, the total 28 nanometer PZT plus 48 nanometer STO capacitance is actually higher than the capacitance of the constituent 48 nanometer strontium titanate. And this essentially tells us that this 28 nanometer PZT ferroelectric was working as a negative capacitor. So this was first reported in 2011. It was reported for a higher temperature, but over the years, many other papers have been reported the similar kind of behavior in a wide range of different materials and at room temperature. So that was the first experimental validation of this concept. Over the last decade, there has been hundreds of publications on negative capacitance. Now here I have tried to list a number of representative experimental work on negative capacitance, categorized in terms of the experimental technique used to probe negative capacitance phenomenon. Now this is not at all a comprehensive list, and there has been a number of great review articles on negative capacitance if you are interested. Now all that being said, the negative capacitance has also received its fair share of controversies. Now over the years it has happened so that there are many times there has been scientific commentaries saying that negative capacitance has been detected or found or discovered. Now how can the same phenomena be discovered, detected or found multiple times? It is because, in my opinion, every time a major publication comes out, there has been a number of articles claiming that the observed phenomena might not be due to negative capacitance effect as proposed, rather due to some second order effects that is coming from the physics of ferroelectrics. Here is a list of a partial list of the papers on these controversial aspects of negative capacitance. Now, controversies are one of the most welcome aspects of the scientific process because the checks and balances ensure that a steady scientific progress is made. This is particularly true for this negative capacitance field as well, because over the years we have seen that our understanding of negative capacitance has changed and evolved a lot. So let me give you an example of this process. So a couple of slides back, I showed a macroscopic picture of how the stabilization of negative capacitance happens in a ferroelectric paraelectric heterostructure. Now, microscopically, it does seem that the picture is much more complicated. So two related papers in this regard are these ones that came out over the last 2 years. Now, it happens so that in a ferroelectric paraelectric heterostructure, the polarization can form very interesting nanoscale polar textures, and within these textures, the static negative dielectric permittivity can occur in nanoscale regions. In other words, in the ferroelectric material, there can be different regions of positive local negative permittivity and positive local permittivity. So this essentially says that the microscopic picture deviates significantly from the macroscopic picture that we started working on for negative capacitance. In other words, negative capacitance is a spatially localized phenomenon within the ferroelectric layer, which macroscopically manifests as capacitance enhancement. So although we are talking about negative capacitance only recently over the last decade or so, negative capacitance was mentioned multiple times in literature even before that. For example, this paper in 1970s by Rolf Landauer, one of the famous physicists from IBM, talked about many different aspects of negative capacitance in ferroelectrics that we are talking about only now. Another aspect of another question that we are addressing right now is that is negative capacitance limited to ferroelectric materials, or can there be other material systems that can also exhibit negative capacitance? So to that end, we are probing a different class of materials called antiferroelectrics. Now, antiferroelectricity are and ferroelectricity are closely related but different. Antiferroelectricity is an electric field induced first order phase transition from a non-polar state and a polar state. On the other hand, ferroelectricity is an electric field driven rotation of the polarization vector without a change in the underlying crystalline symmetry. So we took an antiferroelectric zirconia, and using the pulsed capacitance method, we could see that we have a similar kind of negative capacitance in this antiferroelectric material that one can obtain in a ferroelectric material as well. So altogether, it shows that it suggests that negative capacitance might be a phenomena, a general phenomena across many different material systems beyond ferroelectrics that exhibits phase transitions. All right, and so negative capacitance can also have impact technologies beyond transistor applications. So, for example, there was a recent paper from Professor John Goodenough's group in University of Texas, Austin, showing that the negative capacitance effect can be useful for electrochemical cells. Negative capacitance. There were other papers as well on negative capacitance that can lead to high performance electrostatic supercapacitors, and also can be have interesting application for sensing and biosensing applications. All right, so let's take a step back now and do a high-level overview of ferroelectrics for microelectronic applications. Now, ferroelectrics are most well known for their non-volatile memory applications. However, ferroelectrics are much more beyond that. For example, we have already talked about negative capacitance for transistor applications and beyond, and ferroelectrics can exhibit other properties, for example, plasticity, metaplasticity, antiplasticity, and stochasticity. Now, one of the key things here is to realize that a ferroelectric material in a two-terminal capacitor structure is fairly limited in terms of what application it can enable. On the other hand, we can combine a ferroelectric with a semiconductor in a transistor structure. A transistor has transconductance gain, and as a result, a ferroelectric field effect transistor can enable a wide range of creative circuit level design techniques that takes a full advantage of all the interesting properties that ferroelectric can enable, and in doing so it can enable a wide range of applications. So let me show you such an application where the ferroelectric acts neither as a memory nor as a negative capacitor. So we took a standard ferroelectric capacitor over here and then connected it to the gate of a standard transistor, creating a hybrid transistor ferroelectric transistor structure like this. Now this ferroelectric transistor shows two interesting properties. Firstly, there are abrupt hysteretic transitions in the current voltage characteristics of this device. And secondly, the width and the location of the hysteresis can be changed by changing the voltage between the drain and source. We don't fully understand why these two interesting properties come up in this hybrid structure, but nonetheless we decided to move forward and show an application of this transistor structure for neuron applications. So over here we built a circuit using this hybrid ferroelectric transistor combined with a standard transistor over here. So the details of how this transistor works was reported in this article in IEEE International Electron Devices meeting in 2018. So let me walk you over as to what the properties of this circuit is. So when a train of input comes into this terminal of this circuit over here, the ferroelectric circuit starts spiking over here, and that's why this input is called the excitatory input. On the other hand, when an input train comes, train comes into this terminal over here, in the presence of the excitatory inputs, the ferroelectric stops these oscillations or the spikes. So essentially the neuron gets inhibited by this input over here. So essentially this circuit behaves like a neuron which has both excitatory and inhibitory connections. Now, why is this specific neuron property of inhibition important? So there has been a lot of work that has happened over the last couple of years in deep neural networks, which is the second generation of neural networks. And amazing results has been obtained, superhuman capabilities in terms of text, speech, audio, and video recognition has been reported in such deep neural networks. Spiking neural networks represent the third generation of neural networks, and there has been a substantial interest lately on these spiking neural networks because of two reasons. Firstly, these spiking neural networks encode information in the spike and their timing, and as a result, they can be extremely energy efficient. Secondly, spiking neural networks are more biologically plausible than deep neural networks. Now, one of the essential features of spiking neural networks is that there needs to be a layer of neurons which can be excited. At the same time, it can also be inhibited. Essentially, there needs to be a layer of neurons whose activity can be inhibited by some other neurons in other layers. Now, this specific inhibition is required to obtain high accuracy in terms of learning. And in biology, even in central nervous systems, inhibition is required to control the flow of information. Now, why is ferroelectric spiking neurons interesting? Because specifically in CMOS, we can also build neurons like this. So the first and foremost, in CMOS, we would require tens of transistors to build a neuron. On the other hand, in our case, we are building a neuron with just two transistors, one standard transistor and one ferroelectric field effect transistors. And even in that case, such neurons does not have this inhibition functionalities. And to incorporate inhibition, you need more transistor in it. So in terms of area as well as energy, these ferroelectric field effect transistor-based neurons can be more energy efficient, provided that we can have these ferroelectric field effect transistors at the same advanced technology node as our state-of-the-art transistors. So this was again reported in 2018, and ever since there has been similar concept of implementing ferroelectric spiking neurons using ferroelectric field effect transistors. So what brings ferroelectricity to the forefronts of mainstream microelectronics now? Ferroelectric random access memories based on perovskite oxides has been in the market since mid to late 2000s for niche low volume applications, for example RFID, smart cards, black boxes in aeroplanes, and so on and so forth. Now, as we know, what really created the second wave of explosive industry interest in ferroelectricity is due to the discovery of ferroelectricity in fluoride structure oxide based on hafnia and zirconia. These materials have already been in high volume semiconductor manufacturing for high-k metal gate logic transistors and commodity DRAMs. For example, our phones, watches, laptops all have these oxides in their transistors and memories. Now, computing paradigm today is data-centric, primarily driven by AI and machine learning applications. Now, in this paradigm, embedded memory, in other words, memory that shares the same silicon with its logic counterpart, is the prime currency for computing hardware. Now, arguably, the memory space is very crowded. For example, magnetic and resistive memories have been in development for more than 2 decades now. So why does ferroelectric technology stand out? This is primarily because of two reasons. Firstly, the emerging memories are current driven, for example, the magnetic and the resistive memories, and hence they're very energy intensive. On the other hand, ferroelectricity is electric field driven, and as such, they can be extremely energy efficient in terms of write operation. In fact, the write energy of ferroelectric field effect transistors can be comparable to that of the static random access memory, which is the workhorse memory for embedded application currently, provided ferroelectric field effect transistors are scaled down to the same technology node of the standard SRAMs. On the other hand, compared to the incumbent non-volatile embedded memory technologies based on floating gate transistors, for example, E-flash technologies, ferroelectric field effect transistors can be much cheaper, because to integrate ferroelectric field effect transistors in the front end, you need 2 additional masks only. On the other hand, to integrate the floating gate transistors we need upwards of 5 to 7 additional masks. And as a result, these floating gate transistor based technologies are hitting a wall in terms of economics for high density integration. However, there are important differences between a ferroelectric field effect transistor and a standard high-K metal gate logic transistor. In logic transistors, extreme measures are taken to make sure that the Hafnia and the zirconia layer remains amorphous. On the other hand, ferroelectricity is a structural phenomenon, and as a result, the oxide layer needs to be crystallized. And in an FE-FET, due to the lack of an epitaxial template, these layers are inevitably poly or nanocrystalline, with the crystallite side ranging between 4 to 100 nanometers. So we wanted to understand how the microstructure changes with an applied electric field. So we performed high resolution TM analysis on antiferroelectric zirconia using in situ applied electric fields. And we could clearly see that as the voltage changes at the tip over here, the domains were shifting and coalescing. And even more interestingly, we saw what appeared to be a field-induced reversible phase transition. For example, at 4 volts, we could see an extra line of atoms show up, which disappears as the voltage at the tip is reduced to 0 volts, happening very reversibly. And these microstructural features actually has an important role in determining the functional response. For example, in zirconia, we changed the thickness from 5.4 nanometers to 20 nanometers. And we also determined the crystallite size using glancing incidence X-ray diffraction. And we could clearly see that the critical fields has a negative 2/3 power law dependence on the crystallite size in these materials. So overall, microstructure plays a central role in determining the functional response of these materials. Now, despite all this excitement around the fluoride structure oxides, there are significant barriers to enable ferroelectric devices in the mainstream microelectronic platforms. In my opinion, there are 3 key challenges which are one way or the other related to the microstructural aspects, as I mentioned in the previous slides. Now, firstly, the spatial inhomogeneity due to the nanocrystallinity leads to significant device-to-device variation, especially when the devices are scaled down to the dimensions of the advanced transistor technologies, and there are millions and billions of them in a chip. Secondly, these fluoride structure oxides have large coercive fields, around 1 megavolt per centimeter for sub 10 nanometer thicknesses. It was considered to be a welcome aspect because it leads to immunity against depolarization field for retention. However, this also drives up the operating voltage, making them inconducive for embedded applications. And thirdly, the microstructural features such as grain boundaries and the interfaces are hotspots for defects, which actually leads to poor endurance and reliability in fluoride structure ferroelectric devices, especially when they're integrated on the semiconductor platforms. Now, it is important to note that many of these challenges were also there in the perovskite oxide-based ferroelectric devices, which were all addressed, essentially leading to the successful commercialization of the ferroelectric random access memories. For example, the commercial FRAMs are actually spec'd at 10 power 15 endurance cycles, which is currently unachievable in the state-of-the-art fluoride structured devices. Now, many of these reliability physics aspects are same across these 2 different classes of ferroelectrics, perovskite and fluoride structure oxides. And I believe that the ISAF community, which has the knowledge and memory of what led to the commercial success of the perovskite FRAMs, and the microelectronics community, needs to work together closely to address these current challenges to make it a success. All right, so altogether, I believe that the microelectronics will usher into an era of ferroelectronics. This is because the next wave of the exponential growth of the semiconductor industry depends on how the electronic hardware can support the explosion of the data-centric computing applications. And with all the different technologies that the ferroelectric can enable, these ferroelectrics will take the center stage in data-centric compute hardware. With that, let me thank all the members in our group who were critical for many of the work that we presented, and thanks to all the collaborators and sponsors.